I would say, one of the prettiest places on Earth.
The Green Bank Telescope, or GBT, is the most accurate large-dish radio telescope on Earth. It has a fully steerable base, an array of receivers, and a massive dish covering more than 2.3 acres, allowing researchers all over the world to study some of the universe's great mysteries. In 2013, it discovered an important pair of prebiotic molecules, indicating that some key building blocks for life formed on dusty ice grains floating between stars. The GBT also hosts Breakthrough Listen, a project searching for intelligent extraterrestrial communications.
All right.
To learn how all this works, Brenne Gregory, a scientific data analyst at Green Bank, took me on a special tour to the top of the 485-foot telescope and, on our way there, patiently explained the fascinating field of radio astronomy.
So the best way to think about radio astronomy is to think about light as the electromagnetic spectrum. So we see visible light, that's about 380 to 700 nanometers. And that's the wavelength that allows us to see this optical light. So when we think about radio astronomy, we're looking at wavelengths that are down in the centimeter to millimeter range. So a lot of people like to say radio astronomy is like listening, but it's easier in my mind to kind of conceptualize it as looking at it as you would with optical light, just at a different frequency. And because it's at a different frequency, we need to use different tools than optical telescopes to look at that light. And so those are the receivers that we'll see up on the GBT that allows us to look at that light in a way that our eyes can't see it. Being up in the mountains, a lot of that is for something called the radio frequency interference. So everybody has cell phones nowadays. We have Bluetooth. We have all of these things that make our life easier in modern society. But all of those things are extremely bright to our radio telescope. You can see an 8-watt light bulb with our telescope if it's past Eris, which is all the way past Pluto.
I thought you were going to say like in the Atlantic Ocean or something.
No, in the solar system, at the edge of the solar system.
So if anything's in this zone, it really pops up.
Yes, it really pops up. We can see it in our data, and we have to do something to remove it in post-processing. So being in the mountains allows us to block out signals from surrounding towns. And that's also why you lost cell phone service as you were coming in. So we have the National Radio Quiet Zone, which is a much larger zone that even extends into Virginia. We try to at least understand the transmitters that are happening in that area so that we don't have a cell phone tower that's, say, blowing us out of the water. And then we have a smaller zone with the West Virginia Radio Astronomy Zone, which is 10 miles around Green Bank. And that's where transmitters are much more limited.
It's technically called the town of Green Bank on site?
Yes.
Okay.
So I live in Green Bank. I live in observatory housing. So the observatory provides houses for a lot of the staff, which is great, especially if you're coming here directly out of school or you're not from the West Virginia area. So I live in a neighborhood with 10 other houses of my coworkers. And it's different living here. I came directly from living in cities. I had never really lived anywhere remote before. And so I went straight basically from living in Glasgow, Scotland to living here in West Virginia. It was a bit of an adjustment. It's very quiet. It's a very quiet site, as you can imagine. To be radio quiet, you have to be kind of isolated. The town of Green Bank, I would say, in addition to the other small town here, Arborvale, is on the order of 300 people.
Okay.
So rather small. SETI is the search for extraterrestrial intelligence. We have a program on the GBT called Breakthrough Listen. So what they're doing is they are searching the universe for signs of life, whether this is pointing at certain spots in the sky and kind of observing for a while and then going back and checking that spot again. To date, we have not found any signals. I think everybody would know immediately if we did. They're a really great group on the telescope that have done a lot of work with RFI as well, because a lot of times these signals are actually just radio frequency interference. Because if you think about it, if we're looking for signals, say from a civilization like ours out in the universe, it's probably going to look like our technology potentially, and so the stuff on Earth is probably, it could seem to be extraterrestrial, but it is in fact just from our Earth. Green Bank has been a kind of a site where this has always sort of been looked at. So Frank Drake wrote the Drake equation here at Green Bank, which is the probability of life in our universe, and it's impossible for that equation to be zero because the probabilities of there are stars with planets around them. So already that value cannot be zero. And so this is an area that many astronomers are very, very interested in, and the general public is super interested in, because, I mean, it's nice to believe that we're not alone. I'm going up with one person for a GBT tour. So what we see right now is our azimuth track. So the GBT can actually rotate from -90 to 450. So that way we can track a source across the sky fully, and we don't have to unwrap the cable. On top of there are track covers. And as you can imagine, to move 7 to 10 million pounds, it takes a lot of power. And so as we get closer, you can see there's a lot of grease. So we do actually grease the track and do maintenance on the track regularly. So each wheel weighs, I would say, close to 2 tons. And so they're actually conical in shape because it makes it easier to push. And so all of these design choices were made to make sure that the GBT could continue to observe throughout many years. So as you can imagine, you've got a lot of force bearing down on those plates. So they really have to be bolted down to keep them in place. All right, so what I'm doing here is just locking out and tagging out. So it's letting people know that I'm on the telescope and that we shouldn't move it while I'm on it. It takes a lot of people to keep the GBT moving. There's a lot of moving parts. And each person is very specialized in what they do, because a lot of this equipment, there's not many large telescopes around to be able to learn how to fix this equipment. So everybody gets very good at what they do very quickly. These are some data cables and some power cables. So most of our data actually goes through the pintile bearing. I call it the heart of the GBT because all of the data that comes off the telescope and all that information is going through cables, going down through there, and then the 2 kilometers to the lab.
This is awesome.
Yeah. All right.
We're up.
Yep. All right.
Sorry for hogging the window.
Oh no, go for it. I see this view quite often.
I figured.
So I don't know if you can hear kind of that humming. So that's actually our cryogenics. Our receivers are cooled with helium, and it's held down at the bottom where we started, and then it's pumped up through these cables all the way to the top, where we're going to be at all the way to the top. So we consider a bottle of helium empty at 300 psi, which is still quite a bit of helium. But what you're hearing is kind of the pushback of us pumping that helium up to the top of the telescope. We're at what we call access today. So the GBT has a bunch of different positions. This one is called access because you can access the telescope. And that just means that this catwalk is completely flat and that you're able to walk across it. There are a couple of other positions that allow us to make the dish more flat. So if engineers have to go and work on that. And then we have some called survival, if it's really windy. That dish is a giant wind sail, and so we try to keep it safe. And then we have something called snow dump. So West Virginia, we get a decent amount of snow, and in order to kind of slough off that snow, we'll tilt it all the way over and let it fall. Ice still collects, and so we'll still have to track the sun to melt ice off the dish, but it's a pretty impressive sight to see.
What planet is that?
That's Pluto, so it's at half mast because Pluto is now a dwarf planet. You'll see some student groups will come and raise the flag all the way to the top.
Ooh, looking down is
Yep, so already pretty high up, and we've only taken one elevator.
Oh, okay, we're going more.
Yeah, we're gonna go all the way to the top. So
Yes.
not quite 485 feet, but getting up there. Hello, how are you?
Good, how are you?
Good.
Hi.
All right, here comes that second elevator. It is tilted because our feed arm is more of a triangle position. So you'll see that coming down. From here, it looks like the dish is completely flat, but when we go up, we'll see that it's actually kind of at a big incline right now. Words really can't do the size of the dish justice, but you can see a really cool effect to actually sometimes where rainbows will come through and will hit the side of the GBT. So this will tilt slightly to the side just because of that. So yeah, not too big of a jolt. It used to be a much bigger jolt, and then we did some repairs. So yeah, as it comes up, you'll be able to see kind of the magnitude of the dish, which is, again, about 2 football fields large. Yeah, and here you can really start to see.
My goodness. How often do they have to replace those panels?
So not very often at all. In fact, the missing panel that you see there, so all of the panels in a row are the same. For a perfect surface, each panel would be different, but for cost-saving measures, each one in a row is the same. So if something on the center, so say ice has fallen and damaged a panel in the center, which has happened, we'll switch out an outside panel for the inside. And that way, the outside panels are less illuminated, which is what we use to say like the radiation bouncing off, so they're less illuminated than the center. So we can handle some panels on the outside being injured or damaged.
Wow, we're going up.
So it's quite massive.
So I imagine when it's really windy.
Yeah, so yeah, we have wind limits. So not only do we have wind limits for being up on the telescope, we actually have wind limits for observing with the telescope. So at about 40 miles per hour gusts, we stop observing and we go into survival mode, just because we want to make sure we're protecting the dish.
Protecting the dish, and I imagine you get a lot of jitter too.
Yes,
probably,
exactly. Right? So for some of our receivers that are smaller beams on the sky, in fact, we'll stop observing even sooner than that because the beams will be bouncing so much.
Wow. This is like the view of West Virginia right here.
Yeah.
This
This is, I would say, one of the prettiest places on Earth. And it just happens that we have a really cool telescope in the middle of it.
Is this the tallest structure in the state? Maybe several states around.
Yeah, it might be the tallest structure. I'm actually not sure. That would be a good question.
I don't know what would be taller than this in West Virginia,
Yeah.
right?
In fact, we have inspections done regularly, as you can imagine, for a giant structure. And there's not just giant telescope inspectors laying around. Inspectors laying around. So we tend to use bridge inspectors because it's kind of the same concept, steel beams and all of that. So it's pretty similar idea-wise there. But this is our receiver, so the top of the receiver cabin. So when we think about how we're taking observations, we're thinking about their sources out on the sky, and that radiation is coming and it's bouncing off this massive dish. And then depending on the frequency, it may bounce directly into this receiver that's located there. That boom would be pulled out so that it can directly bounce from the dish to that receiver. Or if it's a higher frequency or anything kind of over 900 megahertz, it'll bounce to the dish, up to, holding your hard hat, up to the subreflector, which is 8 meters across, and then down into our receivers.
That moves to reflect the different bands
Yes.
onto these different receivers.
Yeah, so what it does is it actually moves to reflect the light from that subreflector down into the one that's in the focus. So right now Mustang is in focus. They're doing tests with that. And so we'll rotate this around to make sure that the bandwidth that you're interested in is in focus. So say you're observing a pulsar at L band. So you're looking at about 1500 megahertz in that band range. So that large receiver will rotate to be in the front, and then that way that light that's bouncing off the dish and then bouncing off that secondary reflector is going directly into the receiver. Then it's processed from there and then sent to our Jansky lab to be written in digital form that our observers can then use. We have a wide range of receivers. They are from about 200 megahertz to 116 gigahertz. So it's a wide range of frequency space. So if we're looking at pulsars, we're going to be at the lower end of that band, L band, PF at 800. And if we're looking at, say, star formation, we might be using ammonia, which would be up at about 22 gigahertz. And that would be with our KFPA receiver. So the science that you're doing is very frequency dependent, and that's based off of the fundamental physics of what you're looking at. By having all these different receivers, it means that our observers can actually use different receivers in their sessions, which they've proposed for, or it means that one observer could be looking at star formation for a couple hours, and then immediately we can switch to a pulsar observation. So we're observing 24/7, about 363 days out of the year. We take off Christmas and Thanksgiving pretty much. Otherwise, we're constantly observing. And that's a little bit different from optical as well, because optical, you're limited by the sun. You can't be looking at the stars with the sun. And so we can continue to look during daytime hours. And so something very unique about being in that centimeter and millimeter wavelength range.
Oh wow, doesn't get old coming up here.
No, I've been up here so many times, and each time it's just as inspiring as the first time. What's my favorite thing is watching our summer interns come up here. It's some of their first research in radio astronomy. Seeing them come up here and seeing them realize that this is what they're going to do for the rest of their lives. There's kind of no words to describe that, because you're like, oh, that is a scientist that's going to be studying radio astronomy for the rest of their life. Yeah.
Is that how you felt?
Yeah, pretty much. I came up here, so I got hired during COVID, and so I observed with the telescope, worked for months before I was ever able to come up on the telescope. And I would say I'm actually prefer that I had it in that order, because when I came up, I understood so much about the telescope that I think I appreciated it more than I would have in the first time. The Allegheny Trail runs through there. Actually, we have some races that will run through there that staff will sometimes help out with aid stations. And there's a really cool lookout, actually. You'll go up a road called Slavin Hollow, and then you'll make your way on this ridge, and you'll be able to look out on the telescope. And so if anybody likes to hike the Allegheny Trail, I definitely recommend that. That's one of the coolest views. Hello. Walter, what we can do is we can just walk down, and that will actually give us good shots, and that way we don't have to worry about scans. If that's, yeah, we can definitely do that. Yeah, cool. Thanks. All right. So we're gonna walk down just to make sure that they're able to continue their tests. All right. So just be careful with your steps. We'll walk on down this way.
Yep.
Just being careful.
Yep.
Woohoo.
Oh yeah. Yeah, when I was younger, I had a little thing of heights, and turns out it hasn't fully gone away.
Oh no!
I mean, I'm good.
I still get nervous up here sometimes, and I've like hung from the GBT on ropes. So yeah, so we have a rope rescue team. We go through trainings pretty frequently, and then we'll practice. Usually not high up, but we're ready to do that if we're needed.
Ready to rappel if you have to.
Yeah.
Yeah, if it's windy up here, that would be terrifying.
I've been up here when it's been pretty windy, and it's definitely scared me, that's for sure. I've been with a lot of mechanics who are like, oh, it's fine. I'm like, it's not fine for me. I'm glad it's fine for you guys. If you were to replace one of the panels, usually they would walk onto the dish and do it from on top.
Oh, so you can walk on.
You can, in special cases, yeah.
If you gotta do it, you gotta do it.
Yeah.
Is it just connected in those corners, just pop, pop, pop?
Yeah, so it's connected in a couple places in those corners. So those corners are connected to the actuators, which allow us to push the dish into a more perfect surface. So if you're at high frequencies, your dish has to be much smoother. Arecibo, which was lower frequencies, that it didn't have a solid surface. It had kind of a not a chicken wire, but a mesh surface. At L-band, you can get away with sort of a chicken wire surface because of the size of the wavelength of the radiation. When we get up to our higher frequencies, you need to have close to a perfect dish, especially here in West Virginia. So if we think about ALMA that goes up into like 200 gigahertz down in Chile, they're in a desert. And so that's perfect because you're not looking through as much atmosphere. So atmosphere is one of the harder things for us to work with at higher frequencies because our dish has to be perfect, we have to be pointed really well, and the weather has to be really nice. And for us, weather means dry. Nice weather means dry and clear. And so if it's raining, we'll probably be observing at L-band because we can see through the rain. So if you were to come here and it was pouring rain today, we would probably be observing L-band because we'd see a little bit of that, but it'd be almost like it was not raining at all. So the way it works is actually scientists will propose for time by putting in a proposal at one of our 2 proposal calls during the year. So you will be asking and presenting your science case to the observatory. So you would write a technical justification saying, this is what I want to do. I think I can do it with the GBT, and this is why. And then you would write a science justification saying, this is why my science is amazing, and why it's valuable to the scientific community. Then that proposal will go to our staff to say, hey, yeah, that is technically possible. So yes, you can do that. And then after that, it will go to something called a science review panel. And so that's different scientists saying, yes, this is also scientifically feasible and would be of value to the community. So once you're accepted through that process, you are then given notification that you've been accepted, and then you will be available for scheduling for the telescope. And that is through our dynamic scheduling, which means that if the weather is the right weather for your project, then you'll be able to, you might be scheduled. So we're scheduled 24 to 48 hours in advance. And so say you've put in for a pulsar observing project at L-band, and you've done really well on your scientific proposal, then you'll probably get scheduled pretty rapidly. And that's all depending on all the different proposals that have ever come in to the GBT that are still observing, our maintenance time, and a bunch of other factors. So it's actually, it's difficult to get time on the GBT. And so if you have a really strong science case, then you'll definitely get on the GBT. But sometimes it can be a struggle to get time.
Oh, I can imagine, yeah.
Yeah.
And that's, so people are all over the world.
Yes.
Asking for times. Many of them, most of them probably never come here.
Yes, many people, we do a lot of remote observing. So oftentimes what we'll do is we'll train everybody through remote training workshops, and then they learn how to use the GBT to observe, and then they'll observe, say, from their office in London. And then the next project could be somebody from their office in India. And so it's really amazing. It's a global scientific community that we're able to participate in. We love when our observers will come to visit. So a lot of times people will come to site to visit, and so that they can sit in our control room and actually observe. So this is the GBT dish. So where we're looking at is, it's an offset feed arm. So our feed arm, instead of kind of the traditional we see over with those interferometers where there's 4 struts coming down to the dish, we are in an offset. And so that means that if I stand here in this center area, this 100-meter dish becomes part of a larger 203-meter parent parabola. So that's why it looks non-circular. So you can imagine sort of that you're in a much larger dish for that. And this just allows us to have great sensitivity, and when we're mapping, we don't see the reflections of light bouncing off of those struts. So looking out, you can see that it's a massive dish. And so you can imagine if you're observing that all of these pieces are moving in sync to be able to allow you to kind of receive that radiation in the receiver and to be able to see that data.
Okay, I'm just getting it now. Like the whole thing moves, but then the individual panels.
Yes, yeah. The individual panels can move. And so that's something we call the active surface. And the active surface is activated at C-band, or about 4 to 8 gigahertz and above. And so we do something called out-of-focus holography, where we map the surface of the dish, and then we kind of push those panels into the position they need to be in for a more perfect dish. And when you do that, typically at the beginning of your observing session at higher frequencies. And you have to do it pretty frequently because, I mean, you can feel the sun on you right now. If you can imagine, there's this large structure that the sun is beating down on. So we have thermal deformations. It's a huge structure, so we have gravity deformations. And we have to account for all of these things when we're taking our data to allow for those high frequency observations. And a lot of our scientists here are experts in high frequency. I'm a low frequency observer. I like to stick at like 800 megahertz, 120 megahertz. But these scientists are getting up to about 110 gigahertz. So they're at much higher frequencies.
What are they observing at those frequencies?
So oftentimes, just all the way to the edge of the grate, and that's about as far as we can go. But so they're looking at kind of, yep, that's good. They're looking at star formation. They're looking at molecular gas. They're looking at tracers for star formation. And so you can do a lot of different science in different areas of the GBT's frequency range.
That project changes. So how long does it take for the body to move
Yeah, so we can do project changes in as little as, I would say, 10 minutes. So what happens is somebody finishes up their observation, and then the next person has already been logged on, has set up their control system on their computer. And then what they do then is our operator will change the band. So say one person's observing at L band and the next person's observing at Q band. The operator will change which receiver is in focus and do a couple of other things behind the scenes to make sure they're ready for the next project. And then within about, say, 10 minutes, that next observer can get on and start setting the surface for their observation and start their observation. We're really limited by the amount of time it takes for our turret to rotate or our boom to come out and whatever the operator needs to do. So it's pretty fast turnaround.
Yeah, it is.
Yeah. And that's why we're able to observe for so long during the day, is because of this fast turnaround, and our operators are really good at what they do setting up for these observations. So those catwalks are for our engineers. So every summer our engineers work on our actuators, which you can see our actuators right here. And those are the panels that are the things that are pushing those panels into place. And so things break all the time, much like any electronics. You have to fix them, especially as they break over time. And so our engineers will actually spend the summer replacing parts of those actuators, and they'll be up and underneath the dish. So they'll be in harnesses, strapped in, and walking underneath the dish. And that's when we go to a special position to make it a little easier for them.
What's up? Not many
people can say that they've walked down the GBT. So,
All right.
Yeah, so we were all the way at the top, and we've walked.
Have you walked down it before?
I've walked down it and up it multiple times.
Nice.
The up's a little bit rougher.
Yeah, I bet.
So.
You'll get some floors on your Fitbit doing that.
Absolutely. Here's a good spot where you can see kind of that network of catwalks. So you're harnessed in, and you've got 2 points where all those wires are. You'll put one lanyard on each so that you're constantly connected.
Do you have to be affiliated, or can if a citizen has a really great idea, will you hear those proposals?
So typically for the GBT, it is going to be from the scientific community. Just because of the kind of subscription.
Nature of science.
Yeah, and the nature of science being peer reviewed.
Right.
But that's one of those moments where if it's a citizen is interested in radio astronomy, we always say, come visit our science center and kind of get a hands-on experience there. Because you never know where that interest will lead, whether that's learning more about the electronics or more about the science and what that could mean for someone.
Is that the counterweight?
Yes, that's counterweight.
And I bet that's where a lot or most, the highest concentration of the 17 million pounds is in those.
Yeah, quite a bit of it is in the counterweight. And then you'll actually see there's extra pieces bolted onto the side. And so when building, there was some extra weight that wasn't accounted for. And so in order to have that counterweight work correctly, they had to bolt extra onto the side.
Oh, there's always a little bit of that, especially when you're at this scale.
Absolutely. And I mean, if you think about building the GBT, nobody had really built anything like this before. And so there's so many stories from people who've been around here from the building of just kind of the things that went wrong and how they solved them. It really did take some of the best minds to build the GBT.
Oh, absolutely. Let's pause here and do a recording check.
Sure.
Good?
Yep.
Awesome. Who needs wireless technology?
Exactly. It's funny because I'll go visit friends and people outside of the quiet zone and the GBT area, and they're always like, well, why do you have wired everything? Wired headphones, I have all wired headphones. Instead of using Wi-Fi, we use Ethernet. We just go ahead and plug that directly into our computers and devices. So a lot of adapters. But it's kind of exciting because you know that by doing that, you're helping the observers that are using the telescope be able to see their data with less RFI.
Yeah, I bet you read a lot.
Yes, yeah.
I mean, but you have, like you said, you still have the internet.
Oh, yeah,
you still have smart
internet,
TVs
yeah,
and everything.
yeah.
Maybe not smart TVs, but
Yeah.
you got television.
Absolutely, yeah. It's like living anywhere else. There's just a couple of things that you have to think about a little bit more.
You're not the Amish.
Yeah, no.
We're
very connected to the internet. Sometimes I would say some of us are too online.
For sure. Okay, wow. So this is
our elevation axis. So when we tilt in elevation, what's happening is these motors are moving us in elevation, and these grooves are so that we are able to hold where we're at. So right now we have our stow pin in. So that stow pin is just a giant steel block, and that's what's keeping us from moving, is that giant stow pin.
Just this.
Yeah, I would say instead of just, it's
I know it's substantial,
Yeah,
but
yeah.
but even like those teeth,
Yes.
you would kind of think
That they'd be much
that
larger.
looks just like the teeth on a bulldozer
Yes,
or something.
yeah,
It's
yeah.
like, oh,
And
each
that's
of those is what,
partially
like a
because of this
degree or a
counterweight.
10th of degree or
Yeah. Yeah. So this counterweight helps us make sure that we're moving so if you think about it, we're looking at points so small on the sky. And so we have to be right on source to be able to see that. So we actually use voltage difference in our motors to make sure we're smoothly moving. And that's why we have so many different motors. So there's 2 sets on this side and 2 sets on the other side as well. So able to move smoothly. We can tilt all the way down to 5 degrees. So if you have a source that's about 5 degrees in elevation, we can tilt down to see that. That's about our limit. The mountains are about 5 degrees in elevation. So once you go past that, you really can't see much besides ground. And then that's also where our software and hardware limits are. And so we have a bunch of different limits in place to help prevent us from running into those limits and keeping the telescope safe. But yeah, we can track a source basically from one horizon all the way to the other. That means we can't tilt all the way back the other direction. So we might twist a little bit to be able to do that rather than just tilt, but we can track from horizon to horizon. In the distance to the right, you can see our 20-meter telescope. So this was originally used for geodesy, which is where you look at a quasar in the sky and you know where that quasar is, and you are measuring the Earth's wobble using VLBI to look at those quasars. So your GPS that you probably used to get here is extremely accurate because of that. There's a site in Nyalesa, Norway that does this, and if they were to go offline, your GPS would get about 30% less accurate.
Oh, wow.
This is CHIME, so this is our other telescope on site. So this is the Canadian Hydrogen Intensity Mapping Experiment. They originally were looking for neutral hydrogen in the universe, and turns out it was really good at locating something called fast radio bursts. So fast radio bursts are these bursts of radio that we don't fully understand. In fact, we don't know where they come from. We're working on trying to understand that, but they're really good at catching that and pulsars. The half pipe design is because it's an outrigger, and so it has a main site in Canada and then another site, and we use that for kind of localization of sources.
Are you still into pulsars? Is that still a thing?
Yes, I am. Yeah, I still do pulsar work.
Cool.
I help support pulsars. I've actually learned a lot about them over a couple of years, so it's been exciting.
Are the planet flags, are these to scale, basically?
Yeah, so from the sun flag all the way at the beginning and all the way down to the GBT, it is a 2-scale model of the universe. And so the distances between the flags represent the distances from the planets to each other. And I think if you were to go on this scale where the next closest star is besides the sun, it would be located on the Earth in Guam. That's how far away it is from us to scale. So just to give you an idea of how big the universe actually is. Astronomers tend to think in very different time scales and distance scales than most people. But that's one of those concepts that it's very hard to understand. I still have trouble understanding, is this infinitely expanding universe. Where is it expanding to?
Right.
And I still can't get my brain around it. I know that that's true. I can't conceptualize it because it's too big for me to conceptualize.
Oh yeah, and and before the Big Bang,
Yeah.
like what
was there? To the left, we have the Tidal telescope, which is the 85-foot one, part of the Green Bank Interferometer. The Green Bank Interferometer was kind of the precursor to the Very Large Array. And so an interferometer lets you create a larger dish without having to build a larger dish. So you're using many different smaller dishes to create the idea of one larger dish, and you get better kind of spatial resolution for this. So with the GBT, you just get the one beam on the sky, and these you get multiple beams on the sky. We're also hoping to soon build the next generation Very Large Array. So the VLA is 27 dishes. The next generation Very Large Array will be in the 200s. Right here is our 40-foot telescope. So the 40-foot telescope is an educational telescope. So it's used by students in a program called Radio Astronomer for a Day, and it's completely manual. So a lot of our systems, you use software to observe with. Here you are using a chart recorder and a metronome to keep time. So you can click through the different frequencies in time. So it really gives students an opportunity to understand the basic fundamentals of radio astronomy. And so they go in this little bunker, and then they'll spend, whenever their source comes up, because it's a transit telescope, it can only move in one direction. They need their source to pass over it in the sky. So they'll come out here at 3 in the morning, and they'll come observe their sources to do science projects. So the 140 foot is a polar mounted telescope, and so it was built by people that built ships for the Navy. It would track a source through the sky, so it's not rotating in azimuth like our GBT does. And there is actually a ball bearing that's floating on a thin layer of oil that helps it move across to track across the sky. And that ball bearing was actually determined partially by the size of the tunnels that it needed to go via train to get here. So right now it's currently not being used, but in the past it's been used for astrochemistry, so looking at molecules in space. In fact, this telescope has found many molecules in space. So if you can imagine, you can tilt this dish all the way over, and they'll bring that all the way to the end of that little railroad, and then be able to work at that top level and pull off receivers and switch receivers in.
Oh, wow.
So the way that radio astronomy works is they're heterodyne receivers. At least most of ours are heterodyne receivers, which means they can only see a certain amount of bandwidth at a time. So we have to change receivers to be able to look at different things in the sky. If you were, say, down at L band, which is where neutral hydrogen is, you can't observe the same thing if you're looking at molecules up in higher frequencies at Ka or Q band. And so you would be able to pull those receivers off, replace it with a new one, tilt it back up, and be able to observe.
Like swapping out a lens on a camera.
It's exactly like swapping out a lens on a camera, yeah.